Okay, so let us do a quick recap. Okay, so the first thing is well, I guess this is kind of like a summary of the whole course. So far we began with an a linear code, binary linear code, which is basically a subspace of k dimensional subspace of right. This is how we started, and we had a notation for it, nkd, then d was the minimum distance, there was a definition for that. And all possible nk, I mean all kinds of nkd are not possible. For a given n and k, there are some bounds on how high d can be. Okay, so one of the bounds is basically the singleton bound, which says d is less than or equal to n minus k plus 1. Okay, so this bound is applies, it can be used for linear codes, non-linear codes, binary codes, non-binary codes, anything you want. Okay, so it's a very interesting and important bound. Okay, so codes that meet this bound are called maximum distance separable. Okay, so that is somewhere we saw, and we saw binary codes. There were only 2 of those which meet the MDS bound. What are the 2 binary codes that meet the MDS bound? Repetition code and its dual, right, the even weight code. So those 2 guys meet this. Okay, and then we saw this definition of this Galois field fp to the m, which is finite field with p power m elements. Okay, and p has to be a prime number. Okay, m is some integer, positive integer. And how do you construct it? You construct it by beginning with a, for instance, a pi of x, which is a primitive polynomial in fp. Okay, so fp is an easy enough field. Fp is what? 0 to p minus 1, yeah, modulo p, addition and multiplication. Okay, so this is a easy enough field, and this is a degree m primitive polynomial in fp. I had a definition for it. I also gave you the result that such polynomials always exist. Okay, so you do not have to worry about existence and all that. So once you have that, you can construct fpm in kind of like a similar way, but in a different slightly different style using polynomials. Okay, so what is that? What is the definition? Okay, so you have to look at polynomials, let us say in some alpha, right. I want to look at polynomials of degree less than or equal to m minus 1, and these AIs should come from fp. Okay, so this is a useful way in which to think about the finite field fp to the m, and here addition and multiplication you would do modulo pi of x. Okay, once again it's a degree m primitive polynomial. Okay, so addition is really not, I mean modulo pi of x does not play any role. Addition is just like vector or polynomial addition. Okay, it's no problem, but in multiplication clearly pi of x will play a role. Okay, and okay, and a crucial another way in which you can think about this is that there is one specific element. Okay, in this case you can take alpha itself to be that specific element, which will be primitive in this field. So what does it mean? You can also, since this pi of x is a primitive polynomial, whatever I am using as alpha, that itself will generate the entire field. Okay, so what you can write this as also is 0 1 alpha squared alpha to the power p power m minus 2 should be such that alpha to the power p pi m minus 1 is 1, and then what else, pi of alpha is equal to 0. Okay, so this is another equivalent way of describing the field. Okay, so this notation is called the power notation. This notation is called the vector notation or the polynomial notation. This is useful for multiplication, this is useful for addition. If you have a table to go from one to the other, you are well set in any finite field. Okay, so this is the finite field in p to the power m elements. Okay, there are other results. There are no other finite fields. Any two finite fields of the same size are isomorphic, etc., which makes these very special structures. Okay. So then what did we do? We went from binary linear codes to, let us say, non-binary or q-ary or p to the m-ary or a larger code with a larger alphabet. Okay, so there we saw there was some better flexibility, as in you could get other codes which were also MDS. I gave you some very simple examples. So that was the kind of motivation. So how does the definition work? It is very simple. Again, a linear code over fp to the m is basically a k dimensional subspace of, instead of 0 1 which is binary, you would take fpm n, which is the n dimensional vector space over the field fp to the m. Okay, so that is the way you think of a linear code. Again, once again you will have n, k and d. Okay, so it is a larger field, you have more code words. Okay, the minimum distance is defined differently. Okay, and so there were quite a few motivations to go to these finite fields. So one of the motivation was you couldn't meet the singleton bound in binary. Okay, so that is one of the motivations. The other motivation, which is also equally important, is that there is no easy way to construct parity check matrices for an arbitrary minimum distance. Okay, so minimum distance is also related to the error correcting capability, right. So the error correcting capability is, right. So if I want to be able to correct, let us say, one error, then it is not too bad, but even for correcting two errors, which requires a minimum distance of what, of 5. Okay, you need a minimum distance of 5 to correct two errors. It is not very easy to come up with a generic method for constructing parity check matrices. That was the other problem, we could not really check minimum distance, etc. So I said both problems are solved by moving to finite fields and defining parity check matrices over finite fields. So in fact, as it turns out, you have a parity check matrix over the finite field with elements from fp to the m, and using that we define both a binary code, a p-ary code, as well as a p power m-ary code. Okay, so that was the idea. So we define these BCH codes and Reed-Solomon codes, okay, which basically had a pretty much the same parity check matrix with elements from f2 to the m. Okay, so usually we stick to p equals 2, right. That's the common alphabet here. So how did that parity check matrix look? If you want a design distance d, okay, let us say block length n, I will come to the dimension later, it is kind of defined differently. So if you have a block length n and a design distance d, what do you need to start off? Okay, parity check matrix H, yes, of course, but how do I construct the parity check matrix? You need some alpha, right. So what is that alpha? You have to tell me what that alpha is. You need what? Alpha should have some property. Order should be at least n, right. You need some alpha belonging to some g of 2 to the m whose order is at least n. Why did I need that? Otherwise in my construction I will have minimum distance 2, okay, so I do not want that, right. So I do not want that to happen in my construction. So in the construction you require that alpha belongs to let us say f2 to the m is such that order of alpha is at least n. Okay. Yeah. So, usually it will be equal to n, you can take it as equal to n if you like, that is one choice, it is a certain kind of choice. You can also take some other element, okay, it does not matter. Suppose I have an element like that, then I can construct a parity check matrix which looks like this. So, the first row is 1 alpha, alpha squared, so on till alpha to the power n minus 1. What is the second row? Yeah, alpha squared whole squared, so on till alpha squared raised to the power n minus 1. The third row is alpha power 3 squared, alpha power 3 raised to the power n minus 1, and the last row is d minus 1, you have to go all the way to d minus 1. Okay, so, this is the magic parity check matrix which somehow solves all our problems, at least the way in which we are looking at. We want NKD codes which are good with respect to this bound, reasonably good with respect to that bound maybe, and then then you should be able to construct a parity check matrix for a given error correcting capability. Okay, so, we did not quite see the proof of the error correcting capability yet, but anyway, so let us begin with this construction. This construction solves pretty much all the problems that we are looking for. Okay. So, the first thing we did was to try and understand K. Okay, so here is a parity check matrix. Okay, first of all, the definition of BCH and Reed-Solomon code, sorry for backtracking a little bit. So, this is a parity check matrix, elements are from f2 to the m. Okay, when you define the BCH code, what do? All code words have to be binary as well. Okay, so, you need two conditions for the BCH code. BCH code basically becomes set of all C such that HC transpose is 0, and then what? Yeah, so basically C has to be binary. Okay, so this is an important thing. Another way to describe the same thing is what was said just now, set of all C such C in a larger field, then you have to intersect it with the binary. Okay, so these are both ways of defining this, and the Reed-Solomon code on the other hand has no such restriction. So, here it is simply set of all C in such that okay. So, according to our definition, H is a perfectly valid parity check matrix for the Reed-Solomon code. Okay, even for the BCH code it is a very valid parity check matrix, but the only problem is it is not binary. Okay, so, for a binary code you expect a binary parity check matrix, here you have a non-binary parity check matrix, but in spirit as far as the definition is concerned it is exactly the same, you can definitely give this definition, there is no problem. And we also saw some very simple examples for very small n over GF4 etc., how these definitions play out, okay, and we got some good feel for why one code is contained in the other, which one is contained in the other one, obviously intersecting with a smaller set it has to be smaller. Okay, so BCH is contained in the Reed-Solomon code. Alright, so this is a lot of recap I know, but I think it is good that we did it. If you have any questions, now is a good time to ask about any of these things, particularly assuming that you have seen the tutorial problems a little bit, maybe you thought of some questions, something that is disturbing you.
Sir, how do we exactly transmit this if the alphabet is not from binary?
Okay, so I will come to that. There are several ways of doing it, but okay, let me repeat the question. The question was, okay, BCH code is fine, alphabet is binary, you are transmitting it. What about non-binary codes? Suppose the alphabet here is f2 to the m. How do you transmit alpha squared? How do you do it? Yeah, so there are several ways of doing it. One way is to think of alpha squared basically in vector notation, which is basically m bits, right? And once you have m bits, you can send m bits, it's no problem. Another way to think about it would be, say for instance, instead of, so in digital communication you have these constellations, right? So you have BPSK, which is basically just a binary constellation, you also have larger constellations. If m is say 8, okay, you could do like 256 QAM, then map directly each element of the field to a constellation point, okay, which you will believe me if I tell you that you can send constellation points, right. So it is something like that. Okay. So as a rule you do not have to worry about sending a finite alphabet whatever it is, right, just map it to a suitable constellation, you can send it. Okay. Anyway, so but remember that point in mind, okay. So there is a catch there, okay. So you will see when you look at the equivalent binary code, the picture is a little bit different, okay. But anyway, we will come to that later, but for now this is important enough. Okay, the next thing we saw was K, and for K there were two different results, one for BCH and one for RS. Okay, so for BCH we defined a G BCH of x, which were called as the generator polynomial. Okay. So by the way, I mean, to understand these codes better, to think of each, we have to think of each code word as a code word polynomial. Okay. So how did we do that change? Yeah. So basically when you think of C as a code vector, you are saying C0, C1 to Cn minus 1. I can equivalently think of it as a polynomial C of x, which is C0 plus C1x plus so on till Cn minus 1 x to the power n minus 1. Okay. And then in terms of in the polynomial world, these parity check criteria are very easy to interpret. Basically all the criteria is saying is that any code word polynomial has d minus 1 roots. What are the d minus 1 roots? Alpha, alpha square, alpha power 3, so on till alpha power t minus 1. Okay. And then you go to your minimal polynomials, etc., and then you work it out very carefully. You would get this description for the BCH code. You have a generator polynomial, okay, which is the LCM of the minimal polynomials of alpha, alpha square, so on till. Did I use this notation or did I use some other notation? Did I use this notation? Okay, that is good. Okay. So it is the least common multiple of all these minimal polynomials. So what is so great about the GBCH? So it turns out the BCH code is the set of all C of x, which can be written as m of x times g of x, such that the degree of C of x is less than or equal to n minus 1. Okay, so that also we showed, kind of roughly we showed why that has to be true. It is easy to see also. Okay, for the BCH case, you have the added constraint that C of x has to be binary. Okay, and when alpha is the root of a binary polynomial, it carries along with it all its conjugates also. Okay, so it is very similar to the real and complex scenario. So the entire minimal polynomial has to divide C of x, which is true because C of x is binary. Okay, so that was different. So clearly now it is very easy to count the size of the code. Okay, C of x is all possible m of x into g of x, such that degree is less than or equal to n minus k plus n minus 1. So all you have to do is you have to look at the degree of this g of x. Suppose the degree is n minus k. Okay, I am saying n minus k for some k. Okay, then you can show that m of x has to have degree less than or equal to what? K minus 1. Right, multiplying these two guys, this has degree n minus k. If I want the product to have degree less than or equal to n minus 1, I should have for m of x degree less than or equal to k minus 1. So that is the only constraint. You can take any m of x, right, binary in the case of BCH. Okay, so this is going to be binary, okay, degree less than or equal to k minus 1. Okay, so how many such m of x's are there? 2 per k, and that made very good sense finally, because that is exactly our number of code words in the BCH code, 2 to the power of k, and so k is our dimension. Okay, so this is a nice notation to use n minus k for the degree of the generator polynomial. Okay, so it is a little bit different, because when you say generator matrix, it is always a k by n matrix, but in the polynomial world the generator polynomial has actually degree n minus k. Okay, so it is reverse. Usually the parity check matrix is what will have an n minus k by n. Okay, here the generator polynomial itself has degree n minus k. Okay, so you should remember this distinction. okay. So that was for BCH code, and that is the degree, okay. So dimension equals k, okay. So from here see dimension is equal to k, okay. For Reed-Solomon codes also you have a generator polynomial, but in this case it is much simpler, okay. The reason it is simple is when I say a polynomial c of x with coefficients in f2 power m has a root from f2 power m, then everything is very consistent. The only thing that has to happen is x plus or x minus that root has to divide your polynomial, okay. So we are in characteristic 2, so minus and plus are exactly the same, so you do not have to worry about that also. So the GRS of x becomes a very simple polynomial, which is simply the product of x plus alpha power d minus 1, okay. So I want you to compute, it's very easy computation, the degree of GRS of x, okay. So why am I interested in computing the degree of GRS of x? I am sorry, I should have put a BCH here. Why am I interested in the degree? Because that degree is n minus k, right. For my Reed-Solomon code, if I want to find dimension, all I have to do is find the degree of the generator polynomial, and that degree would be n minus k, okay. So the degree here equals n minus k equals what? D minus 1. So like I said, this matrix solves many of the problems that we wanted. One of the problems was n minus k equals d minus 1, okay. So that clearly shows these Reed-Solomon codes are MDS. Okay. Okay, notice the subtle difference here. In this case, the set of all code words is again a C of x equals m of x g r s of x. Again you have degree of C of x is less than or equal to n minus 1, but you do not have the binary restriction, okay. So what happens for m of x? It is from f2 power m and degree less than or equal to k minus 1, okay. So that makes a big difference between these two guys. Okay, so I think this is probably the last thing we did in the previous lecture. So it's good to go back and revisit this, because this is something new, you may not have seen it before, it's important, okay. But okay, nobody is impressed and happy that we have found maximum distance separable codes, no, you are happy. You are worried about what exam question might come from. That is the problem with learning it in a classroom, okay. Okay, so of course, I mean, to claim really that this is MDS, I have to show you that the minimum distance is D, right. Of course, if I do not show minimum distance is D, it is not really MDS, but I have already motivated it, I have said it is design distance, so I should be able to show minimum distance is D, which is what we will do next. Okay, so the proof is not too bad, it's quite straightforward in various ways, it uses very elementary methods, so we'll say that. So the claim here is minimum distance of BCH RS codes is at least D. Okay. So, I only have to show at least D to claim the MDS. Why should I have to show only it is greater than or equal to D? Yeah, the bound is anyway true, D can never be greater than n minus k plus 1. So, once I show it is D is greater than or equal to that, I already have a D less than or equal to from the singleton bound. So, I can see both and say D equals n minus k plus 1, it is no problem. Okay, so, it works out very easily, but this is what I want to show. Okay. So, to show that what I will do is, okay, let us say we will do it proof by contradiction. Okay, so, the proof is by contradiction. Okay, what is contradiction? You have to assume it is not true and come up with something which is evidently not true. Okay. So, what do I assume is not true? I am going to say, suppose a vector C which is in Fp power m n with weight of C equals W, which is less than D. So, less than or equal to D minus 1 is such that what? H times C transpose is 0. Okay, so, this is my contradictory statement. I am saying, suppose you have a code word C which has weight less than or equal to D minus 1. Okay, so, of course, this is the same as the minimum distance, right. So, minimum distance and weight are the same for linear codes. Why should I also worry about F2 or no, not, I am sorry, F2 power m? Is it enough if I show F2 power m n, or should I worry about F2 also? Yeah, see, remember F2 is contained in F2 power m. So, if I show this, then the binary also comes for free. Okay, both proofs are incredibly similar, so do not have to worry too much about it. Okay. So, this is the idea. Okay. So, what we start by doing is, let us say weight of C is W, let us say the non-zero locations of C are, let us say I1, I2, so on till IW. Okay. So, these guys are between 0 and n minus 1. Okay. So, these are the non-zero locations of C. What do I mean by non-zero locations of C? So, in these positions in the vector C indexed from 0 to n minus 1, C can be non-zero. In other positions, what should it be? Should be 0. Okay, so, that is also assumed. Okay. So, basically C will look like some, you can think of this as some ordered sequence also. Okay. So, that you can imagine that C will look something like 0 for a while, and then it will be something at I1 and then 0 again, and Ci2, so on Ciw and 0. Okay, so, this is a picture that you can keep in your mind. It is 0 everywhere except for the I1, I2 to and Iw position. Okay, the indexing is from 0 to n minus 1, that is for just convenience. You can also keep it from 1 to n, but it is just a small shift. Okay. So, what does Hc transpose equals 0 imply? Okay, wherever there is a 0, that column does not participate in the equation at all. So, we multiply it out and keep only the non-zero terms, you will see you will get a smaller equation than this. Okay, several of the columns will go away. Okay, so, what exactly will be the equation that I get here? Okay, so, you will have, okay, so alpha power I1, alpha power I1 squared, so on down to alpha power I1 power D minus 1, right. This will be the first column. I will write down the final thing later. Second column, alpha power I2, is it right, or am I making a mistake? It is fine now. Alpha power I2 squared D minus 1. Okay. I think I have done an interchange between maybe the way you are used to. So, there it might have been alpha I1 alpha squared power I2 alpha power D minus 1 raised to the power I1. Okay. So, I am just doing the using the commutativity of multiplication, if you will. Okay, so it is not a big deal. Alpha power IW, alpha power IW squared, so on down to alpha power IW raised to the power d minus 1. Okay. What is the dimension of this matrix now? D minus 1 cross W. Okay. So remember that it's d minus 1 cross W times what? Times Ci1, Ci2, Ciw equals 0. When it says 0, it is the all 0 column matrix. Is this clear? This is okay, no? You can go back and check that. I mean, what I might have written here is alpha power I1, alpha squared power I2, so on. Okay, but I can bring the I1 inside and take the square outside. It's okay. It's the same thing. Okay, so W is less than or equal to d minus 1. So I can choose to keep W rows and drop the other rows. Okay, so you might ask why I would want to do it, because then I would get a square matrix, and square matrices you have determinant, which is a much more well studied and understood idea, which is what we are going to use next. Okay, so since W is less than or equal to d minus 1, I can without any problem only keep W rows here and drop the remaining. Okay, so if you only keep W rows, okay, what will change here is this will become W rows, and what will change here, instead of d minus 1 I will have W. Is that okay? That is fine. Okay, when I did this matrix became square. All right. Remember, my alpha is such that order of alpha is at least n. Okay, so clearly there is no danger of any of these things repeating or any of these things becoming equal to the other. So what will happen in the square matrix is alpha power I j, okay, will not be equal to alpha power I j prime. Okay, so in this case all these exponents are, all these entries are different. Okay, so this square matrix has a name, you might have seen it before when you solve any matrix determinant problem. It is called the Van der Moen matrix. Okay, so and its determinant is a well studied problem from ages ago. Okay, so this matrix, when this condition is true, well, even if it is not true, I guess it is called the Van der Moen matrix. Okay, and one can show its determinant goes to 0 only when, okay, let me put it the other way, as long as this condition is satisfied, its determinant is non-zero. Okay, so you can prove it using so many ways. You think of it as you can subtract the two columns and then you will see there is a common factor that is pulling out. So in fact the determinant of this has a very simple expression, it is simply the products of the form alpha power I1 minus alpha power I2 or alpha power I1 minus alpha power I3. So it is the product of all those things. Okay, so basically the final statement that you can make now is it is a Van der Moen matrix and the entries are not the same. So determinant of that square matrix is non-zero. Okay, so now that implies, I am sorry, what is this that by the way? This guy. Okay, the fact that none of these things are the same, okay, and it has that shape, it became a van der Waals matrix with non identical columns. When you have that, the determinant of that matrix, okay, of the square matrix is not 0 and you have a contradiction. Okay. So, if you have a matrix with a non-zero determinant, clearly you cannot have a non-zero vector in its null space, that is not going to happen. Okay. So, we have our minimum distance results. Okay. So that gives us is greater than or equal to d. For RS, again it is greater than or equal to d, but then what happens because of this? Okay, so what did we show? We also showed that d has to be, okay, so by the singleton bound it cannot be greater than n minus k plus 1. Okay, so you have here two different things which tells you that for the RS case it has to be in fact equal to d. Okay. For BCH you cannot in general say that it is equal to d, okay, because you do not have any result on the degree of the degree of GBCH. Okay. In this case the degree of GRS becomes equal to d minus 1. So, you know from there that there is a nice bound on k, it does not work. Okay. All right. So, to summarize, for BCH codes and for Reed-Solomon codes, you have block length n, okay. So, and you need a primitive element, okay. So, remember order of alpha should be at least n and alpha is from some f2 power m, okay. So, you have to pick m in such a way, okay. So, what is an easy way of picking such an alpha, or what is one way, or not say easy, what is one way of picking such an alpha? Is there any ready made method that you can think of? So, my question basically is, how do I pick m? Is there a very smart way in which you can quickly pick m?
Fun.
Suppose I tell you n is 1000, what will you take m as?
M is
2 per m minus 1 equals m.
Equal to m, okay. So, you take n equal to 2 per m minus 1. What if there is no such m, for instance 1000, clearly there is no such m, what will you do?
Next.
What has to be greater?
2 per m minus 1.
2 per m minus 1 has to be greater than n. Why should 2 per m minus 1 should be greater than n? What is the idea there? Okay. So, the idea is you go to m large enough so that 2 per m minus 1 is at least n, and then take alpha to be a primitive element of that. Okay, if you take it to be a primitive element, what do I know the order is? Order is equal to 2 per m minus 1, and that would be greater than n. Okay, so that is the strategy that you can use. Okay, so basically the idea here is to pick m such that 2 per m minus 1 is greater than or equal to n. Okay, so that is the first step, and then take alpha belonging to f2 power m as a primitive element. So, once you take it to be a primitive element, what will happen, order of alpha will be 2 power m minus 1, which is greater than or equal to n clearly by choice. Okay. So, for any n you can go to a large enough m and get the alpha satisfied. Okay. So, parity check matrix is identical. Okay. So, the same for both. Okay. But what happens to the generator polynomial? Okay. For BCH you have the LCM of the LCM formula. For Reed-Solomon, what do you have? Is that okay? I think Rakesh has fooled around with the AC system, and I think it is totally off now. Not getting any air conditioning at all. Are you responsible for that or no? Okay, so I mean, maybe I should draw some lines here to demarcate what I am saying. Okay. What else should I add? And the next thing I should add is for dimension and minimum distance. What about dimension? The dimension for the Reed-Solomon code is simply n minus d plus 1. Okay, so that you can quickly read out, because degree of the generator polynomial is simply d minus 1, and that is n minus k. So, you do the shift, you get n minus d plus 1. The dimension here is a bit more complicated, okay, but it will be definitely smaller than n minus d plus 1. In fact, if you pick m as greater than 1, it will be definitely much smaller, much smaller. What you can show here is a very simple bound. Okay, you can show that the dimension is greater than or equal to. Okay, so let me see how do you come up with the bound on the dimension of BCH codes real quick. Okay, what can happen in the worst case? In the worst case, all these guys can be different, but that cannot really happen. Why cannot that all of them cannot be different? Because alpha and alpha square has the same primitive polynomial, right? So, same minimal polynomial, I am sorry. So, for the odd numbered guys, you might have all different minimal polynomials, in which case what should you do? You will be taking the product. Okay, when you take the product, it will become, the degrees will add. Okay, so I need a bound on the degree. What is the maximum degree of a minimal polynomial? If I take an element of f2 up to power m, what can be the maximum degree of a minimal polynomial?
At max m.
At max m, no, it cannot be greater than m. Why cannot it be greater than m? Yeah, I think I gave these results, maybe I did not prove it very rigorously, you might have forgotten it. I said the degree of a minimal polynomial has to divide m, right, you remember. Yeah, exactly. So, if you take a particular element, you have to count the number of conjugates it has. In no circumstances can it have more than m conjugates, right. So, if you keep on squaring it, once you go to 2 power m, you will definitely repeat. Okay, so it cannot have more than m conjugates. So, that is an idea. So, based on that you can do a bound. Okay, so you can say it is greater than or equal to something, and think about how you might want to do that. I am not going to write down the exact expression. You have to look at the number of even guys here and then do that times m and subtract. Okay, so it is a possibility. Definitely it will be smaller than n minus d plus 1. Okay, so then the minimum distance. Okay, in this case it is equal to d. Here it is at least. Okay, so I should point out that the exact dimension and minimum distance of BCH codes are tough to compute in most cases. Okay, well, dimension may not be that difficult to compute, you have to do just some simple operation. Minimum distance is a much more difficult problem. Okay, so it continues to be a research problem, maybe not of so much interest as it was before, because it is an old code, people do not use these things so much anymore. Okay, for many cases, many interesting practical cases, it has been solved. Okay, only for some extreme cases people still keep working at it. Okay, so that table kind of captures the picture roughly. So hopefully it's clear. Are there anything that's disturbing you? It's simple enough at this point, right? There's nothing. I guess the proof here is the only thing which is a little bit more involved, and the proof just comes from this van der Waals matrix property. Okay, so essentially these kind of matrices have a non-zero determinant as long as the columns are not identical. Okay, so that's the basic idea, and using that you build a code. You can see this is the most crucial thing in the entire construction of BCH codes and Reed-Solomon codes, right? I might have started at one point, I would have gone on here and there, but ultimately this is the most crucial aspect if you think about it very carefully. All the other things you can manage. Okay, it's interesting that you have a generator polynomial, it's interesting that code words have a very simple description, etc., but this is the most crucial property which gives you minimum distance. I don't know the first paper that, I mean the question was how was the first construction, how did people think about it, I don't really know, I mean, but this is the heart of it. I know for instance Reed and Solomon, when they described their construction they did not use this language, they used completely different language, which is also very interesting. I think there is a tutorial problem in your tutorials on that, you can take a look at it. It's an interesting way of doing it. Okay, so let's see some examples. We're going to see a whole bunch of examples, and then that will drive home the point. Okay, so we'll begin with the simplest and most interesting example. We'll begin with GF16. Okay, so we'll do constructions with GF16. So when I say we'll do constructions with GF16, it imposes some restrictions on the block length. Okay, what is the maximum plausible block length that I can use? If I say I'm going to limit myself to GF16, 15, right? I can't go beyond 15. Okay, so the order of the primitive element is 15. I cannot go beyond 15. Okay, so keep that in mind. So I'll start with alpha and GF16 being primitive. Remember, alpha power 15 is 1, and then let's say alpha power 4 is 1 plus alpha. So that would be the primitive polynomial I chose for the construction of GF16. So I get that. Get the field. Okay, so I've been talking about design distance D. Okay, so it's much more common to use error correcting capability, designed error correcting capability. Okay, so what is designed error correcting capability? Okay, so if you want a designed error correcting capability of 1, what should your design distance be? 3. If you want a design error correcting capability of 2, what will be your 5? Okay, so basically it means you only have to look at design distances which are 3, 5, 7, so on. Okay, you don't have to look at 4. 4 doesn't give you anything new. Okay, you can't correct anything interesting. 4 gives you something interesting maybe, but doesn't give you anything which is useful for error correction. So usually the design distances are 3, 5, 7, so on. Okay. All right. Okay, so let's start with 3. If you start with 3, so 3 is not really that interesting because we already know how to do 3, right? You know how to do it, it's not so difficult, but still we'll start with 3. Okay, if it is 3, then I'm going to describe my parity check matrix in a very simple way. I don't want to write this whole parity check matrix over and over again. Okay, so I'll simply say I'll write some very shorthand notation. So hopefully it's clear to you. Okay, I'm not going to write all the rows in all generality. Maybe I'll write some 1 or 2 rows, and hopefully you can interpolate from anywhere. Okay, so let's say D equals 3 for My parity check matrix is going to look like what? You will have powers of alpha, so on, then alpha squared, that is it, right. The last guy is going to be alpha power n minus 1. Is that okay? So, you have just 2 rows and n columns. Remember, n is going to be always less than or equal to 15 for me, because I have limited myself to G of 16. You can go all the way to 15 if you like, okay, whatever n you like you can go, you can stop there. Okay. So, this is d equals 3. So, for d equals 3, what is the G BCH? Okay, G RS is really simple, x plus alpha times x plus alpha squared. So, G BCH will simply be the LCM of 2 minimal polynomials. What are the 2 minimal polynomials? Minimal polynomial of alpha and minimal polynomial of alpha square, which is also the same as the minimal polynomial of alpha. So, simply you will get the minimal polynomial of alpha itself, and that happens to be, yeah. So, you would get x power 4 plus x plus 1. Okay. So, this is the minimal polynomial of alpha. Okay. So, the RS code, okay, we now know is n comma, what is k? Okay, what is the dimension for the RS code? Is it 2 or n minus 2? Confusing, right? Remember, degree of the generator polynomial is the best way to start when you want to find dimension. Okay, first find the degree of the generator polynomial. What is the degree of the generator polynomial? 2, and the 2 equals what? N minus k. So, k is n minus 2. Okay, so n minus 2, and we know the minimum distance in this case is equal to 3. So, these are the 3 parameters for the Reed-Solomon code. Okay, so now I am going to ask a very difficult question. How many code words are there in this Reed-Solomon code?
N power.
How many code words?
2 power n
16 power n minus 2. 16 power n
16 power n minus
16 power n minus 2. Do you agree? Okay, is that okay? How many number of code words is what? How many of you think that is the most bizarre thing you have ever heard? Okay, does it make sense? 16 power n minus 2. How do you list out all the code words of the RS code? You have to take this m of x. M of x is what? That is like the message polynomial, whatever. So, m of x. You have to take m of x of degree less than or equal to k minus 1, okay, or degree less than or equal to n minus 3, and multiply it with this g of x. How many possible m of x do I have? 16 power n minus 2. Okay, so, it is 16 power n minus 2. So, remember these are codes over g of 16. That is another way of thinking about it. These are codes over g of 16. So, moment I say dimension is k, how many code words do you have? 16 power k. Okay, dimension is n minus 2, you have 16 power n minus 2 code words. Suppose I say n is 15, how big is that number? How many digits will that number have?
2 power 52.
2 power 52.
17 digits. 17, 18.
So, it is a big number. That is what I want you to convince you about. Take log 10 of that number. Okay, so, n is 15, 13 times log 10 of 16. Okay, so, log 10 of 16 is fairly large, right. So, you have that many digits. Okay, so is it okay? Everybody okay? All right. So, it is a large number. Okay, so that is what I want to impress upon you. It is a really large number. So, So far we have been talking about a 7,4 code, we had just 16 code words, it's a small code. We are now talking about a huge code, okay, and you have a very compact description for it. What is the compact description for the huge code? You simply multiply any polynomial with x plus alpha into x plus alpha squared, okay. So the number of bits, so number of message vectors is 16 power n minus 2. So if you want to count the number of message bits, you have to write it as 2 power 4 into n minus 2, okay. So if n is 15, you are looking at 52 bits, okay. So you can take 52 bits, convert them into 13 symbols over g of 16 and then make this polynomial m of x and then multiply m of x with g of x. Remember, the multiplication has to be done in g of 16, you can't just change that all of a sudden. So you will get one big polynomial c of x, that will be a code word polynomial, okay, right, and that will have 15 symbols from g of 16. If you want, you can convert that back into bits, you will get how many bits? 60 bits, okay. Is that reasonable? Okay, think about what it means. Alright, so that is the picture in the Reed-Solomon world, okay. What happens in the BCH world? Okay, it is again a little bit similar but slightly different also, okay. If you want to write down the 3 parameters, block length is n, fine, n is less than or equal to 15. What about dimension? N minus 4. And what about minimum distance? Okay, the only thing I can say at this point is greater than or equal to 3. Can somebody come up with maybe a way of showing that the minimum distance will be equal to 3? What is the way of showing it is equal to 3? Okay, what is the only way of showing the minimum distance is equal to 3? You have to find a code word of weight 3 which is binary also, right. There are two problems there. It has to be binary and then code word of weight 3. I am saying there is a code word of weight 3 staring at you in the face right there on the board. Which is that code word? Can you identify on the board a code word of weight 3?
It should be 1.
Remember, always it is good to think of code word polynomials instead of code word vectors. Okay, what are all the code word polynomials?
All the polynomials.
All the polynomials which are products of g BCH of x, okay. So for instance, if I take m of x to be simply equal to 1, then what is definitely a code word? X power 4 plus x plus 1 is a code word polynomial, okay. What is the weight of that code word polynomial? 3, okay. So there is an answer staring you in the face right there, okay. That is the code word of weight 3. Is that okay? It's a little bit of a switch to go from vectors to polynomials suddenly, okay. Think about what I said once again very carefully, okay. How do you find all the code words of the BCH code? We have this polynomial notation, right. So we take m of x and multiply with g of x. What is m of x? It can have only binary coefficients and it can have degree less than or equal to k minus 1, okay. So you remember I wrote that down, okay. But remember, binary is 0 and 1, one such valid m of x is m of x equal to 1, okay. So basically 1 with zeros everywhere else, okay. You just take that, simply get g BCH of x as a code word and that has weight 3, okay. So you can see easily that the minimum distance will be equal to 3, okay. So now how many code words will this have? Two power n minus 4, okay. So this seems a little bit more manageable, you are not too scared of it. Even if n is 15, 2 power 11 is 2048, it is not so big, okay. You are not too scared. It is only 11 bits, you can take 11 bits and then map it to 15 code word bits directly by the multiplication, okay. So I will draw a picture of that also soon enough, but I want you to see that. that okay? Any questions? So if you have to come up with code words of these codes, okay, so if you want to generate, let us say 10 different code words of the BCH code, how will you do it? Yeah, you will find 10 different message polynomials, okay, so that you can easily come up with. Okay, so remember a code word polynomial C of x is m of x times x power 4 plus x plus 1. It is a very easy multiplication. Remember what is this m of x? m0 plus m1x plus so on till m10 x to the power 10. What are these mi's? mi's are either 0 or 1. Okay. So as simple as that. Okay. So you have 11 different message bits, you fill them up with an arbitrary 11 bit vector, anything you like, you will get a message polynomial, you can call it a message polynomial. You multiply with your generator polynomial, you will get a polynomial of degree less than or equal to n minus 1, okay, whatever your n was. In this case you will get 14, okay, degree less than or equal to 14, and that will have binary coefficients, and those are your valid code words. Okay. So this is one way to think about it. Here what would you do to get a code word polynomial? It's a little bit more slightly different, right? Okay, so this is n equals 15. I am sorry. Yeah, so the picture will be very similar, except that this polynomial will not be x power 4 plus x plus 1, it will be x plus alpha into x plus alpha squared, and the coefficients will go not just till 10, it will go all the way till 13, okay, well 13, so 12, right. So you multiply with g of x, okay. So if you want, I can write that down. So if you pick n is equal to 15, your code word C of x is going to be m of x times x plus alpha times x plus alpha squared, okay, and your m of x is m0 plus m1x and each of these mi's are now from F16. Okay. All right. So if I have to draw a picture, I think a picture is also important here to see something. Let me quickly draw a picture. Okay. So this is how a BCH code, the 15, 11, 3 BCH code, this is how it would work. Okay. So you would have 11 bits. Let's call it a message vector m or a message polynomial m of x. You are going to do an encoding, and you would get how many bits? How many bits?
15 bits.
15 bits. You can call it a code word vector C or a polynomial C of x. This will be, let us say, m of x into g of x. Let us say this is how you are choosing to do your encoding. In fact, there are other ways in which you can encode, but this is maybe a way that we pick. Okay, so that is 15 bits, and it will go out. This is how the encoder would operate for the BCH code. Okay. What would happen for the 15, 13, 3 Reed-Solomon code over GF16. Okay. You would first have how many bits? 52 bits, which you can think of as a binary message. What will you do here? You go from F2 to F16. What is this notation? F24 goes to F16. What does it mean? So, I take 4 bits at a time, then convert it into a symbol over F16 or some alpha power some I. Okay. So, each 4 bit vector represents some alpha power something. I convert to that. After that, what do I get? I get 13 symbols. Okay, I have to call it symbols. Symbols are elements of F16. I could call it a message vector M or a message polynomial M of x. Okay, and then what do? I use my encoder. Okay, once again you could do multiple things here. Let us say we do a multiplication with, you get a code word C, or C of x would be M of x into G of x. Okay, remember the G of x here is different, so I should maybe say what the G of x here is also. Here it is x power 4 plus x plus 1, here it is x plus alpha, x plus alpha square. Okay, it can be implemented, right? Even if you are doing like a chip in FPGA or VLSI, you can do it, or you can write a computer program to do it, MATLAB program, etc. And you can actually do this. It's not a very difficult thing. And then what do? Yeah, so you have to do a F16 to. Okay, so I'm running out of space here. So let me erase some more of this. Okay, so it's good to think of it as being converted back to bits. Even if you are doing something else here, you can go from F16 to F24. Okay, so you do that, you get 60 bits. Okay, so this is how the encoder would operate. Okay, so there are several differences between these two pictures. Many of them are easily apparent to you. Okay, so here you have a much longer number of bits. You are dealing with a longer block. Okay, here you are dealing with a shorter block. There is a subtlety about minimum distance which I want to particularly emphasize with you. Okay, so when I say minimum distance is 3 here, what does it mean? If I take any two code words that are going out here, they will always be separated by at least 3 if they are distinct. If they are the same, of course they are the same. Okay, so if they are distinct, then they will be separated by at least 3 bits. What will happen here? Where does it apply? Okay, here it applies, right? If I look at any two symbols that are going out here, they will be separated in at least 3 symbols. Okay, so that's different from saying 3 bits. Could be more than 3 bits, but it will be at least 3 bits. What about the outer picture there? Suppose I say from 52 to 60, I look at two 60-bit things that are going out here. What will be the separation between those two? At least 3. Okay, all I can guarantee is at least 3, right? Because 3 symbols can be different in exactly only 1 bit position in the worst case, and that would differ only in only 1 bit. Okay, so if you see what you have achieved overall, you are going from 11 bits to 15 bits with at least a difference of 3. Here you are going from 52 bits to 60 bits with once again at least a difference of only 3. Okay, so ultimately when you use a Reed-Solomon code, which is MDS and all that, the final binary code is far from being MDS. Okay, so 6052 has an n minus k of 8. Okay, but you still only have a minimum distance of 3. Okay, so that's a bit of a catch. You should be aware of that. Okay, so when you use it, you don't get the binary MDS code suddenly. Okay, so you've gone to a larger field and we've solved the problem. So you don't necessarily get a binary MDS code, but it's useful in several other ways. Okay, so this notion of symbols having a minimum distance is also very useful. Okay, so it's not that it's useless, but You should be aware that finally when you do bits you do not get the same MDS property, okay. It comes only at the F16 level. Okay. Okay, so let's do a slightly more complicated example. Okay, so it's only 3 minutes, so it's good to do a complicated example. Suppose I want a BCH code with n equals 60. Okay, suppose I want a BCH code, so just to do a comparison here, suppose I want a BCH code with say n equals 60 and d equals 3. Okay, how should you go about doing it? First step is to find an m such that 2 power m minus 1 is greater than 60. What would be that m? 6. So I can start with an alpha n f64 which is primitive and define my parity check matrix, etc., etc. Okay, if I do that, okay, it's just d equals 3. Okay, so my g BCH of x will be what? It will be LCM of m alpha and m alpha squared, but again alpha and alpha square have the same minimal polynomial, so it will be simply m alpha of x. And what will be m alpha of x, which will be the primitive polynomial I used for the design of f64. So in particular, what will be the degree of this? Six, right? Degree equals 6. Why am I worried about degree? Why did I ask this question about degree? Yeah, I want to find the dimension of this code. If you want to complete this picture, I should know k, right? What is the g of x? So g of x has degree 6. Okay, so what is this code now? N equals 60, k is 54 and d is at least 3. In this case, believe me, it's true, you can go see the tables, minimum distance will be equal to 3. So now I want you to tell me why I asked this question. Why did I ask this question? I wanted to compare
54 you can
the final binary thing you got with the Reed-Solomon construction and the direct BCH construction. What would you say is better? The direct BCH is better. Why is that? You are getting 2 more bits as opposed to Reed-Solomon. Okay, but what would be a disadvantage of the direct BCH bit? For 2 more bits, is it worth it? What are you paying for 2 more bits? All the math will have to be with g of 64. For just those 2 bits, you have to do all the arithmetic. Well, at the encoder it seems like there is no arithmetic, but at the decoder, believe me, there will be arithmetic over g of 64. Okay, so you have to now do operations over g of 64 for just those 2 more bits of information. Okay, so in Reed-Solomon you can work with just g of 16, which is a much smaller field, much smaller table to keep in mind. Okay, so we will stop here for this lecture, we will break and then we will pick up again for the other one, but this is a good picture to have in your mind. We will see more examples, we will see many more examples to drive home the point, but I think this is an important enough point to know, I can say that.